on the f-divergences between hyperboloid and Poincaré distributions, please.
Okay, so first I would like to thank Koichi Tojo for having swapped with me not to have 3 talks in a row. And I think Tojo explained a lot about the Poincaré distribution as a background, so I will be able to proceed very smoothly. Initially, my co-author, Professor Kazuki Okamura, was intending to come, but he couldn't make it for some reasons, and he was kind enough to prepare a few slides. So it's just 10 slides, but I think it highlights two nice concepts. And one of the concepts is very general and not can be applied in many different settings. It's the concept of maximal invariant, and I think it's very powerful, and it has been underrated in machine learning and statistics. So we will see how to use it in this framework here. Okay, to give a little bit of background, what we would like to do is to do statistical analysis where the sample space is hyperbolic, like let's say the hyperbolic disk or upper plane. And the reason for that is that in machine learning, there's a lot of works now. It's a hot topic to try to embed discrete structures, discrete graph structures, weighted graph structures into continuous spaces so that you can apply downstream tasks like deep learning things. And these have been called hyperbolic embeddings because in hyperbolic geometry, there's a proof that you can embed with a low distortion any tree into hyperbolic space with 1 plus epsilon for any epsilon precision resolution. So it has been the theorem by Sarkar in 2012. And once we have embedded discrete graph into hyperbolic geometry, let's say the upper plane, then what we would like to do is we have datasets of points living in the upper plane, and we would like to do the same kind of statistical analysis as we do in Euclidean space, like how to learn mixtures, how to cluster, how to make hypothesis testing, and so forth. And to do that, we need a good notion of distances between the distributions that we will learn on the point sets. So if we look at the literature of parametric probability distributions that have been defined on hyperbolic geometry, we can find that in the 80s, there are some papers who consider the hyperboloid model, which is also called the Minkowski, in that case, the Minkowski space. And this paper was basically an analogy of the von Mises-Fischer distribution of the sphere, but for the hyperboloid model of hyperbolic geometry. And Frédéric Barbaresco in 2019 also defined what is called the Suryo-Gibbs distribution on the Poincaré disk, using this method of invariant, and where you have the Fisher information metric that coincides with the Poincaré hyperbolic Riemannian metric for that family of distribution. So in the work of Tojo and Yoshino in 2000, they propose this kind of 3-parameter distribution on the upper plane, where you have 3 parameters that can be also recasted as a 2x2 positive definite matrix living on the cone, and you can write the PDF even with the matrix parameter or with the triple vector. Okay, and this is the density that has been shown formerly, and they also in this session presented the Q-deformed Poincaré distribution as well. Okay, so we are interested into analyzing what will be the f-divergence between 2 parametric hyperbolic distributions. And we are going to investigate 2 families. So in general, we will stay in the 2D hyperbolic plane. So we have xy living in hyperbolic space. And in that case, the f divergence for a convex generator f just writes as a p f of q over p as usual, but with xy. So one of the first theorems that we have is that the f divergence between 2 Poincaré distributions, so remember that the parameter theta and theta prime are 3D or 2x2 SPD matrix. Every f divergence or any f divergence that you may imagine can be written as a function of 3 terms, and the terms as a determinant of the matrix for theta, the matrix for theta prime, or the trace of matrix inverse of the matrix. And the way that we can prove such a theorem is by showing that first the f divergence is invariant by the action of SL2R, so that we have we have this invariance here, okay, and then we show that every action invariant function on the upper plane is a function of those three terms by the framework of maximal invariant of the action. So the notion of maximal invariant is something that is working for any group action, and it has been applied in statistics by Eaton. There's a book also that considers transformation models in statistics. The idea is very simple, and it's also summarized here. So we take a function f, and we will say that the function is invariant under the group action by J if we have fjx equal f of x. So far, no surprise, it's just the notion of invariance. So now, if I look at the orbit of the f value for the group action G, I will have I will partition my space into orbits, and if all orbits have different values, then I will say that it is a maximal invariant. Okay, and the key theorem of Eaton with a short proof, half a page proof, is to show that any invariant function is a function of a maximal invariant. So let's say that you have a difficult problem and you know that it is invariant to some action, and then you have an easier problem that you can solve but is maximal invariant. Then you know that your difficult problem is a function of the easy solution that you get. Okay, so it's very powerful methods because you don't have to look at the geometry of things like that. It's really algebraic proof that lets you write f of x as a function of the maximal invariant. Okay. So, for example, if we take the Poincaré distribution defined by Tojo and Yoshino, and we take the Kullback-Leiber between two such things, we will find that the Kullback-Leiber can be expressed like that. And you will find terms here, which are those canonical terms, the free terms that make the maximum invariant of the SL2R action, group action. If you take the square Hellinger, which is an f-divergence for this generator, you will find this expression here. And so this can be also written somehow as a function of those three terms. So in the sense that if you rewrite this f-divergence, you will also find that it is this can be expressed as a function of those three elementary terms. And if you take the chi-square, the Neyman chi-square f-divergence, you will find this thing. Okay. Now I want to introduce another kind of distribution. This time I will take the hyperboloid model of a hyperbolic geometry, not the Poincaré upper plane. And this has been studied in the late 80s and 90s by Barton, Nifstels, and Jensen. And we consider this Lobachevsky space. We take this inner product, which we call the Minkowski inner product, where here you have the signature of your inner product, and we define the parameter space like that for the PDF like that. Okay, so this is if you look at this paper, you will get such a thing, and we are going to introduce a notation x tilde to be this lifting. Okay, we have x1, x2, and we put on the hyperbolic sheet. Okay, and we have we take this absolute value notation to be the square root of the Minkowski inner product. So now this is the second theorem that we obtain in the paper. We say that the f-divergence between two such hyperbolic distributions, theta prime, can be expressed as a canonical, as a function of three canonical terms, which are Minkowski inner product of the pairwise parameters. Okay, and in the paper you can show also that this divergence between hyperbolic distribution can be explained with a notion of side-angle side theorem. So in Euclidean geometry, if you want to check whether two triangles are congruent, you can check that all edges lengths are the same and all interior angles are the same, but it's only enough to consider one vertex and two edges and the interior angle. And this, why is it enough? It's because of the SIS or side angles side theorem. And in this theorem, you have extension into hyperbolic geometry. And here it pops up as f-divergence somehow by taking this origin here. Okay, so this is going to be congruent in hyperbolic geometry, and this is also explaining this theorem. So to get again some explicit formula for f-divergence between two hyperbolic distributions, we will get it for the Kullback-Leibler, square-Linger, and chi-square as before, and we will see that we can express it as claimed by the three canonical terms. So last, there's a correspondence between the Poincaré distribution and the hyperbolic distribution. This is a correspondence that you can highlight. And for this map, you can rewrite the square of the Minkowski inner product as this. Okay, and then for every f divergence and every two distribution with parameter theta prime in the Poincaré distribution or the Poincaré upper you will have the f divergence, which is equivalent to the f divergence between two hyperbolic distributions with equivalent parameters. Okay, so there's a nice correspondence between those two families who are defined on different models of hyperbolic geometry. So this is just some references to conclude, and if you have any questions, I will be happy to answer. Thank you.
Thank you.